Hello everyone. Today we are taking the same that is the already we seen in previous 2-3 videos related to Boolean algebras and some basic laws. Same we continuing the same part previously we seen already 2-3 videos. I will take the some examples on today's video, that is the example on logic gates as well as in some Boolean algebra. Why we are taking? Because we have to solve the different types of problem, then we getting the laws, then we getting the logic gates, how it works, all that problems then we solve. Hence I am choosing the today's topic, that is the examples on logic gates and Boolean algebras. Means you will be gets perfect laws, as well as you will perfect on laws, and then we will easily solve different types of problems on Boolean algebra as well as in logic gates. Here the one diagram will be shown, that is the logic circuits. Logic circuits hai, it also depends on the some Boolean expressions, and it also depends on some truth tables. Means sometimes the truth tables given, you have to prepare the logic circuit. Sometimes logic circuit will be given, then you have to prepare a truth table. Same logic circuits, you have to write one Boolean expression, and it will be also depends on the some logic circuits, and Boolean expression also some depends on the truth table. And uh, using of truth table, you have to define the Boolean expression. Sorry, I was given one sentence, but using of truth table, it is very difficult to prepare the logic circuit. Logic circuit given, then you have to prepare the truth table. It is very easy. And this is the some given some tree diagram. It will be depends on with each other. That is Boolean expression will be depends on truth table. Truth table also depends on Boolean. Same logic circuit and Boolean expression will be depends on each others. And before moving the some examples, I'll clear the concept of some logic circuits. And here I was connected one link of that video, that is the animated video from the, that is the related to logic circuits, learning circuits. And you check the some animation video, because it will be clear the concept of that, how it works with some circuit diagrams. Already that part already we seen in previous some videos, but it is the very easy to clear the concept by using of some animations. And hence I was connected one link from learning circuit video. I'll play it.
The following program is brought to you by Element 4.
Low, represented by a 1 and 0, called a NOT gate. Building blocks of fundamental logic gates include invert, also called a NOT gate, and, Nand, or, NOR, exclusive OR, called XOR, and exclusive NOR, called Xnor. We've learned that digital electronics have two states, high and low, represented by a 1 and 0 respectively. A 1 is when the higher voltage, often 5 volts, is being supplied, while a 0 is when 0 or near 0 volts is supplied. Let's take a look at the first logic gate, the inverter, also called a NOT gate. They invert whatever signal they get. Input a 0, it outputs a 1. Input a 1, it outputs a 0. Set up as an analog circuit, you can think of it like this, with the switch being the input and the light being the output. Input a 1 high signal, the switch is closed, and power is diverted through the switch away from the light. The light is off, output is low, a 0. Input a 0 low signal, it's like the switch is open and power is supplied to the light. The light is on, output is high, a 1. Input high, the light is off, the output is low. Input low, the light is on, the output is high. While NOT gates have only one input and one output, the rest of the gates we'll discuss is an AND gate. On our AND gate, the inputs are labeled A and B. To show all the different possible states of a gate, we use a truth table. It's called that because in digital logic, a 0 equals false, while a 1, if both inputs are low, zeros, the output is low. If one but not both inputs are high, a 1, the output is low. Both inputs must be high for the output to be high. Here's an analog circuit representation of an AND gate, where each input is represented by a switch and the light represents the output. If both A and B equal 0, the light is off, output is 0. If A is 1 but B is 0, the light is off, output is 0. If A is 0 but B is 1, the light is still off, output is 0. Both A and B have to be 1s, on, for the light to be on, outputting a 1. The next gate can be made by combining an AND gate and a NOT gate. It's a NAND gate. Notice how the symbol for NAND just adds the little circle from a NOT symbol. Think of it as adding an O for no. So a NAND is basically an inverted AND gate. Therefore, its response is the inverse or exact opposite of an AND gate. Anywhere an AND gate is low, a NAND is high. And where an AND is high, the NAND is low. When A and B are high, a NAND gate is not high, but the inverse. Output is low. In all other conditions, the NAND output is high, where an AND output would be low. Here's another analog circuit example to help illustrate the function of a NAND gate using switches. With both inputs 0, both switches being open, power goes to the light and it is on. Output is 1. Either switch being closed, a 1, power still goes to the light. It's on. Output is 1. Both switches must be closed, A and B being 1s, for the power to the light to be bypassed, the light off, outputting a 0. Let's move on to OR gates. In an OR gate, if both inputs are low, output is low. If A or B is high, the output is high. Since when either A or B is high, the output is high, when both are high, the output is still high. Let's take a look at an OR gate as an analog circuit. If A and B are both open, zeros, there is no path to the light. The output is 0. With either switch being closed, a 1, there is a path to the light, and it is on. Output is 1. Both switches being closed, 1s, just provides extra paths to the light. It's still on, outputting a 1. Now for the NOR gate. Just like with an AND and NAND, a NOR gate can be made by combining an OR and a NOT gate. So a NOR gate behaves inverse of an OR gate. With a NOR gate, A nor B can be high for the gate output to be high. If A and or B are high, the gate output is low. Again, we'll see this in action in an analog circuit. The A and B switches have to be open, zeros, for the power to go to the light, outputting a 1. If A is high, 1, power is routed away from the light, output is 0. If B is high, the same. Both switches being closed, 1s, still routes power away from the light. It's off, output is still 0. Lastly, we'll cover the exclusive gates, XOR and Xnor. To get the symbols for XOR and Xnor, we need an X for exclusive. Take both symbols and add a line across both inputs, Xing them out. An exclusive or XOR gate is high only when either input is exclusively high. If the inputs are the same, both low or both high, an XOR outputs low, 0. If the inputs are different, the output is high, 1. An exclusive NOR or Xnor gate is the inverse of an XOR gate. An Xnor gate requires the inputs to be the same for it to output 1, high. We can use the three-way switch circuit we made in a previous episode to demonstrate the function of an Xnor gate. With both switches low, zeros, the light is on. Output is high, a 1. If both switches are high, 1s, the light is on. Output is high, a 1. If the switches are flipped opposite each other, the light is off. Output is 0. In the three-way switch episode, I showed an alternate way of wiring the circuit that yields the opposite results, just like an XOR gate. If the lights are flipped opposite each other, the light is on, a high output of 1. If the lights are both flipped on or off, the light is off, a a low output of 0. Logic gates come packaged in ICs with multiple gates in each chip, and usually have at least one pin for input voltage and one pin for ground. Since NOT gates only ever have one input and one output, that leaves room for 6 NOT gates in a 14-pin IC. So these chips are called hex inverters. XOR and Xnor gates always come with only 2 inputs. However, AND, NAND, and NOR gates often come with more than 2 inputs. For these ICs, the logic of each gate remains the same. In these AND gates, all 3 or 4 inputs of a single gate must be high for the output to be high. If none or only some are high, the output is low. With these NAND gates, if none or some of the inputs of a gate are high, the output is high. But if all inputs are high, the output is low. With these NOR gates, all 3 or all 4 inputs of a single gate must be low for the output to be high. If any or all of the inputs of a single gate within the chip are high, then the output of that gate will be low. Well, hopefully that gave you a better understanding of logic gates. Working with logic and digital circuits can get confusing.
And this is all our about the video played by the learning circuit, and this is some animation video, and I hope you clear the all the logic gates. I'll take the one example here. Given a one logic circuit, given the one expression, that is the a plus b and c, that is the a or b and c, and you have to draw the diagram. That is the here a or b, hence we are drawn here, and c, that is the one connection, and output of that or gate, this is given to the AND gate, and this is the basic diagram. Another one given a plus b c, a plus bc plus d bar, that a is the or with bc and b in c in between the AND gate, and d is the complement, that is the d bar, means a that only one input, b and c is the AND gate, and output of that AND gate is the given for the OR gate, here is the, and d bar, that is the NOT gate, and that 3 inputs given to the OR gate because 3 terms are here, and this is the diagram of some logic circuit. Again here we taken AB plus that AC bar, the AB in between AB multiplication sign, that is the AND gate, A and B AND gate here, and A and C there is a bar, this NAND gate is given, total bar is the given, hence A input, C input, NAND gate, that bubble indicates the NAND gate, and the whatever the AND and NAND gate output, it will be given the plus sign, that is the indicates OR gate, it will be given to the OR. Another one example, that is the in bracket a plus b bar, second bracket c plus d, and third bracket c bar, sorry, third term is the c bar. Check the first term, a plus b bar, means here is the OR gate, but bar is the given, means that is the NOR gate, that is the OR, here is the indicator, the bubble means NOR gate, that is the a and b is the input, bubble indicates, that is the bar, that input is the given because here is the sign of multiplication, that is the output of the this gate will be given to the AND gate. Second one c plus d, that is the c or d, c and d, that is the OR gate, will be output connected with AND gate, and only c complement, that is the c, that is the connected NOT gate given to the AND gate, and whatever the output will be generated by the AND gate, because here is the sign of multiplication, that is the AND gate. We move towards some examples on Boolean algebras. This is some laws with OR and AND gate, that is the indicates, that is the AND gate and OR gate. So AND and OR gate, whatever that's laws will be given, that is the De Morgan distributive, associative, commutative, double negation, complement, identity law, XOR, XNOR, all that laws will be given here. That is the XOR get X XOR Y, that is the, it will be right, that is the XY plus XY, that laws will be given here, and it will be helpful to reduce the sum equation. Here we taken the example, simplify the expression AB plus some mistake will be here. Okay, AB plus A in bracket B plus C, say plus B in second bracket B plus C. This is the example. Then you have to apply the distributive law here given in second and third term, that is second and third term. And then what will be gets the equation, that is the AB. We multiplied the in bracket, that is the AB plus AC. Here is the BB and that BC, that is apply rule, that is the BB means that is the repeated terms, means omitting terms, you have to reduce that term and we will take the single term, and we get the equation AB AB AC, that reduced term B and BC. Again you have to apply the term, that is the repeated terms AB and AB, and you have to take only one term, that is AB AC B plus BC. Again the rule is the given B plus BC is the B, that term will be reducing. Then here we taken AB AC plus B. Again AB plus B, then you have to take the only B. Same rule here we applied. Same again apply the rules here also. Then he takes the B, means remain only B plus AC. Means this is our expression and we got the simplified equation. Hence we are studying that Boolean algebra, because in the using of the laws we will be get the, and it is a very simplified and much possible expression. And this is the logical diagram of AB plus A, and after that final logical diagram means you will get the clear concept, that is the logical diagram of given equation, and after reducing the logical diagram of this equation. And I hope all of you clear that, and already previously 2-3 videos we already taken that such type of examples. Another one example we are taken here, that is A plus C, mm, in second bracket AD plus AD plus AC plus C, and you have to reduce that equation. This is the original equation. Then you have to apply the distributive law in the equation, and here is the AD plus AD. Then we'll take the common A, in bracket remain D plus D, AC plus C, that is the distributive law. And then complement and identity law, already previously we seen the law, that is the A plus C, and here is the A remain D plus D will be gets, that is the repeated term, since we gets the remote that term AC and C. And now here, that is the A plus C is the given with the bracket of multiplication A. Then and here also the term, that is the AC plus C. Hence we taken the common A term from the common from the A plus C, that is the cumulative and distributive law. And after reducing the, we get the equation, that is the A, that is the A plus C plus C. Hence that is the repeated terms, what will be the repeated terms we remove. Then multiply in the bracket, that is the AA, AC, and C term is as it is. That A will be gets only A. Here C will be gets common, that is the A plus 1, that is the again identity law, it will be 1. Hence will be gets the equation A plus C. Yes, this is the your equation, and after that using of Boolean laws we got that equation. Here also some examples, that is the simplification purpose given example. A in bracket A plus B plus in bracket B plus AA, third bracket A plus B. Now here we are applying the sum distributive and important law, that is you have to multiply with each bracket a b. Here we taken the a will be common from the outside, it will be remain b plus a, and here is the a plus b. That is the idempotent law we apply. Now here we taken the a b term, because a term will be gets 1, remaining b plus a as it is and b plus a b as it is. Then we multiply with brackets ab ab aa bb ab, and after that repeated terms will be gets cancelled, that is ab ba, that a will be as it is, and the ab term is repeated, hence we taken only ab, and bb also repeated terms, hence we taken. Here also given for the age, then complement the identity and remove the bb. Okay, then ab plus ab, here we identity law apply for the that single term and ab. Now next step what will be going on, the ab, the a terms will be gets outside, that what will be remain b, the 1 and b, means we get the ab plus a, means a plus ab, that is the commutative. Then again we apply the here commutative law, that a for a and ab plus a plus b, that is the distributive law, and we get the equation a plus b, that is the complement and identity. This is the means this this much type of laws you have to apply on that one expression, then you have to reduce. This is the equation, and after the reducing this will be gets, means you have to know the all the Boolean laws clearly, then you will clear the, and then will be solve the Boolean algebra. Again we are taken here example ab plus a in bracket b plus c plus bracket complete plus b second next bracket b plus. This is the original as it is we are taking, then multiply with bracket, that is ab ab ac bb and bc. Idempotent law is say that bb means b, then here we taken ab ab ac bb means, and that is the idempotent law b and bc. Again here is the repeated terms ab ab, you have to take the only one term ab ac b bc. Okay, then absorption law, that is the b plus bc, that is the repeated term, hence we have to take the only b from that. Already we used in different examples also in this type of laws. Then ab ac and b. Again absorption law is the ab plus b, that is the b, that is the b plus ac, we get the simplified equation, and that is the given in example diagram. And after the reduction, before reduction Boolean expression and after reduction Boolean expression, that is b plus ac, that is b only single with and ac. Another one example here is the given, that is the x plus y, x plus y plus x plus x bar plus z bar. Then sorry, this is the by mistake, this bar will be here and this bar will be here. The we take the here first two brackets x plus y bar, that is the multiplied, that is the x and x y bar, y x and y y bar. Then here applying the x means x, that is the idempotent law, means what will be remain x x y bar y x, and y y bar will be, that is the law, it will be 0, means what will be that here will be takes that common terms, x is as it is, from x here taken common terms, that y bar plus y, that is the 1, means what will be remain x plus x, that is x plus x, means that is the x, This is the reduced equation for first two brackets. Then you take the third bracket also, that is x plus x plus y bar and x bar plus z. Then you getting the first two bracket, that is the x, that is x bar plus z. Then again we apply the multiplication rule, x bar x z. By distributive law, x bar here we taken 0, that is the what will be remain xz, means that is the xz is the our final equation of the these expression. This is the when you do using different types of law, you will get such type of final equations. Another one expression by using Boolean rules. The expression is ABC plus A bar B plus ABC bar. Now here is the some missing terms. Then we are applying the that is the here we are applying the C plus C bar means 1. The missing terms, hence we get the A bar B and C plus C bar, that is the 1. Hence what is the final equation, that is the AB plus A bar B. But A plus A bar, that is, and B will be gets outside. So A plus A bar, that is the 1. The we get is the output is the 1. In this equation here, AB terms will be gets common, then remains C plus C bar and A bar B as it is. We simplify the we get the equation B. This is all about the examples of today's, that is the examples on some logic circuit and Boolean algebra. We'll stop here and we'll see the different types of and another part of Boolean algebra. Thank you.